So linear regression works well if the data is approximately linear, but there's many examples where linear regression performs poorly. Here's one where we have a curve that is clearly nonlinear. This is an interesting one where we seem to have a linear relationship that is flatter than the linear regression indicates, but there's one outlier. Because we are minimizing quadratic error, outliers penalize you over proportionally. So outliers are particularly bad for linear regression. And here's a case where the data clearly suggests a very different phenomena from linear. We have only two input variables ever being used, and this one has a strong frequency and a strong vertical spread. Clearly a linear regression model is a very poor one to explain this data over here. Another problem with linear regression is that as you go to infinity in the x space, your y's also become infinite. In some problems, that isn't a plausible model. For example, if you wish to predict the weather anytime into the future, it's implausible to assume the further the prediction goes out, the hotter or the colder it becomes. For such a situation, there's a model called Logistic Regression, which uses a slightly more complicated model than linear regression, which goes as follows. Let f of x be our linear function, then the output of logistic regression is obtained by the following function. 1 over 1 plus exponential of minus f of x. So here's a quick quiz for you. What is the range in which z might fall given this function over here and any linear function of f of x over here? Is it 0, 1? Is it minus 1, 1? Is it minus 1, 0? Minus 2, 2, 2? Or none of the above? The answer is 0, 1. If this expression over here, f of x, grows to positive infinity, then z becomes 1. And the reason is, as this term over here becomes very large, e to the minus that term approaches 0, 1 over 1 equals 1. If f of x goes to minus infinity, then z goes to 0. And the reason is, if this expression over here goes to minus infinity, e to the infinity becomes very large, 1 over something very large becomes 0. When we plot the logistic function, it looks like this. So it's approximately linear around f of x equals 0, but it levels off to 0 and 1 as we go to the extremes. Another problem of linear regression has to do with the regularization or complexity control. Just like before, we sometimes wish to have a less complex model. So in regularization, the loss function is usually the sum of a loss of a data function and a complexity control term, which is often called loss over the parameters. The loss over data is typically quadratic loss, as we discussed before. And the loss of parameters might just be a function that penalizes the parameters to become large, up to some norm p, where p is usually either 1 or 2. If you draw this graphically, in a parameter space comprising two parameters, your quadratic term for minimizing the data error might look like this, where the minimum sits over here. Your term for regularization might pull these parameters towards 0. It pulls it towards 0 along a circle if you use quadratic error, and it does it in a diamond-shaped way for L1 regularization. Either one works well. L1 has the advantage that parameters tend to get really sparse. If you look at this diagram, there's a trade-off between W0 and W1 in the L1 case that allows one of them to be driven to 0. In the L2 case, parameters tend not to be as sparse, so L1 is often preferred. This all raises the question how to minimize more complicated loss functions than the one we discussed so far. are there closed-form solutions of the type we found for linear regression, or do we have to resort to iterative methods? And the general answer is, unfortunately, we have to resort to iterative methods. Even though there are special cases in which closed-form solutions may exist, in general, our loss functions now become complicated enough that all we can do is iterate. Here is a prototypical loss function, and the method for iteration will be called gradient descent. In gradient descent, you start with an initial guess W0, where 0 is your iteration number, and then you update iteratively. Your I plus first parameter guess will be obtained by taking your ith guess and subtracting from it the gradient of your loss function at that guess, multiplied by a small learning rate alpha, where alpha is often as small as 0.01. I have a couple of questions for you. Consider the following 3 points. We call them A, B, C. I wish to know for points A, B, and C, is the gradient at this point positive, about 0, or negative? For each of those, check exactly one of those cases. In case A, the gradient is negative. If you move to the right in the x-space, then your loss decreases. In B, it's about 0, and in C, it's pointing up, it's positive. So if you apply the rule over here, if you were to start in A as your W0, then your gradient is negative. Therefore, you add something to the value of W, you move to the right, and your loss has decreased. You do this until you find yourself in what's called a local minimum, where B resides. In this instance over here, gradient descent starting at A would not get you to the global minimum, which sits over here, because there's a bump in between. Gradient methods are known to be subject to local minimum.